Is that my screen is visible? I'm sharing my screen. Anyone please respond. Is that my screen is visible?
Yes, sir.
Okay, fine. So this is the APB signals. Up to this we have discussed in the yesterday class, right? So P clock is used for bus clock source, right? So every transfer it will take rising edge of the clock. Okay, that is pause edge of the clock. And also we have a reset 10 signal. Reset 10 signal is the reset operation purpose we are using. So in this reset operation, why we are typically it is a system based reset. Okay, if you are setting that reset value should be 0, that means it is asserting the reset operation. At that time, what are the signals are there like P address, P select, P enable, write, read data. So write data and then P strobe, P ready. All these signals are assigned to 0 during reset condition, right? If this is an active low signal, so that means if you assign 0 means it is in asserting the reset condition. Okay, at that time all signals are initialized to 0. Now, reset 10 is 1 means it is deasserting the reset signal. So, deasserting means so um, you're not you need to assign the values to the below signals like PPROT and then PSEL, PENABLE and PWRITE, PWDATA, PSTRB. All these signals manually we need to assign the values. Okay, and then P address signal. Address signal it is typically 32-bit wide. So 32-bit wide means so it can support up to 2 power 32 address signals. Okay, so that is the AP address signal. And PPROT. PPROT is the protection signal. See, it is operated in secure level, normal operation, and privileged operation. So based it is a 3-bit. Okay, PPROT 0 it is operated in secured region, and then so it based on the 2 down to 0. So PPROT of 2 means it indicates that normal operation. PPROT of 1 means it is indicates that privileged operation, and PPROT of 0 means it is a non-privileged access. Okay, so I will explain that privileged, non-privileged, and normal access. Normal access means it's a normal operation like write read operations how we are doing. So that is the normal operation. Privileged access means suppose one master is communicating with the other slave. Okay, so then other master is there. So this is the my master one, and this is the slave. Okay, so here we are communicating each other, but other master is came into the picture, and then so this master want to communicate with the same slave. If it is having privileged access, okay, so then it is it is disconnecting the communicating with the master one and establish the communication between the master 2 and slave 1. Okay, so that is called privileged access. Privileged means so it gives some priority to that master. Okay, so that is called privileged access. And slave select signal. Slave select signal, if it is 1 means okay, p select signal should be 1 means you are selecting some particular slave. You are selecting one slave. So that means so we have multiple slaves. So slave 1, slave 2. So in that any one of the slave is selecting. So depends upon the p select signal. And then P enable signal. P enable signal. So in the previous cycle, we are selecting the slave. Okay, after the next cycle, we are enabling that. Then it is accessing the so in initially P select is 1 and then P enable should be 0. Okay, in the next cycle, we are maintaining that P select is equals to 1 and P enable is also equal to 1. That means it is entered into the access phase. Okay, whenever it is entering into the access phase, So it will starts the communication between the master and slave. That's it. And then P write signal. If it is 1, okay, so if it is high means it is doing that write operation. That means master is putting the data into the slave. That is the write operation indication. And then P write signal should be low. That means it is doing the read operation. That means slave is sending the data to master. So that is called as read operation. And PWDATA. PWDATA means write data. So it is also supports like that address P address signal. So same way PWDATA means write data. This write data bus it is also supports up to 32-bit byte. And I told you that write strobe signal because you are sending different bytes of data. Suppose 32-bit data only you are sending. That means byte 0, byte 1, byte 2, byte 3. So in this, what which bytes are there, and then in which byte is valid data is available. That will defines that this p strobe signal. P strobe signal defines that which byte having a valid data. Okay, so that defines the strobe signal. Okay, and PREADY. So PREADY is generally transferring from where we are getting the PREADY signal from slave to master. Okay, slave is sending this PREADY signal. Whenever you are setting P select equal to 1 and P enable equal to 1, at that time next cycle we need to slave need to send the P ready signal should be 1. Okay, then only it will stop the communication. So okay, I have received the data. So slave is received the data. Then the master is stopping the transfer. And then PR data. PR data means read data. What is the read data use? So we are reading the data from slave. Okay, that means slave is sending data to master. Okay, so that is also it is used as 32-bit wide. Okay, so 32-bit C P address signal is also 32-bit. PW data is also 32-bit, and PR data is also 32-bit. Okay, so that is here address data. All these are 32-bit wide range of signals we are using. And then PSLVERR. PSLVERR indicates that if you are transferring is okay, so then normal transaction is happening. That means my master is sending data to slave. So I am putting the data, and slave is also sending data to master. Okay, so that means the slave is ready to receive the data, so then it will send that okay response. Okay, so transaction is completed, then it will send the okay response. If it is having any error like p slave error is there, okay, this signal is setting in between the write transaction. So then, so write or read transaction, if you are receiving in read transaction, p slave error should be asserted means it is setting to high means you are receiving incorrect data. Okay, so that indicates that this P slave error. P slave error indicates that the transfer is okay or it is showing some error. So while receiving the data from slave to master, okay, so then at that time the slave error should be high means, so at that time it indicates that error transaction is happening. Okay, anyone? Are you understood what I am saying?
Yes, sir.
Okay, fine. So in these signals, we are having different type of signals. Control signals. Control signals are P select, P enable, P write. So all these signals are see. So P select, based on the P select only which slave we want to communicate each other. So that is depends by P select signal and P enable signal. So during transfer phase or access phase, So I need to transfer the data. So for that purpose, I need to enable the slave. So then only I will communicate in between the master and slave. So that is the control signal. And then if you are doing the data, putting the data from master to slave, or you are getting the data from slave to master. So depends upon the P write signal, we are doing the write or read operation. So that's why the P select, P enable, P write all are called as control signals. And address or data signals like P address, we are putting that 32-bit address bit. And similarly, write data is also 32-bit and read data is also 32-bit. Okay, all these signals are, see, address is there and write data is there. So at that time, address signal is also there, write operation is also there. That's why it is having address or data signals, we are saying that. But during read operation, we don't need any data signal. So we are putting the address, based on the address, it is getting the data. Okay. So and then handshake signal, that means P ready signal. If you are setting the P ready, your slave is ready to receive the data. And then P slave error. If you are getting the error signal at the reading time, you are receiving the garbage value. See, these are the data bus notations. How the clock signal are used. See, APB protocol has two independent buses. Okay, so one for read data, other for write data. Okay, both are 32-bit wide range data buses we are using. Okay, so that is the data buses we are using. Data buses, we are having two independent data buses. One is read data bus and other one is write data bus. Both are 32-bit. Okay, PW data is there and PR data is there. Okay, so both are independent write read signals. Okay, so for write read buses we are having. So these two buses are 32-bit wide we are using. And so this diagram, whatever the signals we are there here, so signals and bus timing conventions we are using in AMBA protocols. How they are showing different signals and related to clock, we are explaining here. What is the clock? Clock defines the sampling reference where data is transferred and where you are starting the data transfer. Based on the clock only, we are saying that. See, in this APB protocol, each and every time rising edge of the clock only, we are initiating the transactions, either selecting the slave or enabling the slave. All these things are doing at pause edge of the clock or rising edge of the clock. Okay, so that is called as clock signal. And then see, this is shaded or slant region. See, this is the high to low region. This slant is undefined value. There is no value for this value. So that means meaning that extract exact signal level during those regions does not matter and then must not be sampled here. Okay, so this shaded region, we don't have any data, we don't have to sample here. Okay, there is a garbage value here, this shaded region. So then that is a not a matter. Okay, so if you are sampling the data at that time, or no problem, if you are unable to sample the data, that is also not a problem. That is the transient region. And then see, this is the shaded region we are representing, transient or undefined region. And then bus stable state. So and high to low, low to high, you know, right? So this is the high signal and we are going to low. That is the high to low notation. And similarly low to high, so slantly it is going there. Okay, this region we don't care about it. So this region we are sampling the data or not sampling the data, there is no problem in that. Okay, so that is the here bus stable means we are maintaining stable data. So during P select, P select is equals to 1. At that time, we are maintaining P address should be stable, and then PW data should be stable. Okay, whenever P enable equal to 1, we need to maintain all these signals stable, like P select, P address, PW data. all these signals we need to maintain stable. Then only we will transfer the data. See, while bus to high impedance, that means you are having this is the bus. Okay, this is the stable data. High impedance means nothing will be doing. Okay, that is high impedance state we are getting. That means nothing information we are getting. Not getting either low value or not getting the either high value. That means 0 is also not getting and 1 is also not getting. At that time we are getting high impedance value, that is the bus state to high impedance state. Similarly, bus changing. That means one data is changing. See, this is the bus. You are changing the data. So here data 1 is there and here data 2 is there. That is the bus change representation. Okay, and then bus high impedance to bus change. Okay, bus stable state we are doing. Initially it is in high state. After that it is maintaining the stable address or stable data, a stable bus we are maintaining. See, this overall diagram, what clarifies here means APB timing signals, how we are sampling the signals, and then how we are tolerating the glitches or transitions. Okay, based on the signals only, we are explaining these glitches and transmission signals. Okay, give me 1 minute. Okay, I will. Fine. Am I audible? All of you?
Yes, sir.
Okay, fine. Okay, all these are signals notations. So this is also signal notations in APB protocol. Same signals, but so clear representation only we are seeing here. Clock signal, I told you that. Okay, there is a clock signal here. How the clock signal is communicating. So every passage of the clock, that means rising edge of the clock, we are changing the signals notations here. Okay, this is the rising edge. That only we are indicating here. Okay, so that is the clock signal. This is high to low. So high to low. So here only see this passage of the clock only we are changing that. Up to this we are maintaining high. After that is going low. And then transient. So this region, transient region, high impedance state to we are changing to transient state. So this shaded region don't get that data. So it is undefined data. We are having proper data or not, we don't care about that. And low to high. This is also low to high signal representation. Bus stable state means we are maintaining valid data throughout the transaction. So that is the valid data and then bus stable state we are mentioning. And then bus to high impedance state. This is the bus data and then high impedance data we are maintaining. And then bus changing. I told you that this is the data 1 and this is the data 2. So this data change, this is the bus change representation. So just do the into mark here. Then this is the data 1 and this is the data 2. And here into mark here, this is the data 3. That is the bus change signal representation. And then high impedance to stable bus. Okay, we are maintaining high impedance and stable bus we are representing. Okay, so in APP we are doing a write transfer signals. Write transfer, how it is doing the write transfer. Every transfer at least two cycles it is needed, right? For write transfer also at least two cycles are needed. In this write transaction or write transfer, we are having two types. One is with wait states and other one is without wait states. So with no weight states and here with weight states we are representing. So in setup phase only we are transferring the data. That means in the rising edge of the clock only it is changing the transaction. See, this is T naught cycle. During T naught cycle, so during first cycle, all signals are idle condition. See, there is no address here, there is no write data here, select signal also 0, and then enable signal also 0. There is no data here, and PREADY is also not high. So during this idle condition, nothing will be happen here. Okay, so idle condition, all signals are, that is the default condition. Default is idle condition. Idle condition means we are maintaining all signals are 0. During T1 to T2, one clock cycle, I am maintaining valid address here. Okay, so here valid address, and also my P write signal should be high. Okay, P write should be high means I am doing the write operation. And then P select signal also high. So, and enable signal should be 0 only still. And then we need to maintain the valid data here also. After the next cycle, we are maintaining the address is valid, and then write signal is also 1, P write signal also 1, P select is also maintained stable, and then P enable should be 1. During P enable state, address, write and select should be maintained stable. Okay, we are maintaining stable data here. And here data 1. So whenever PREADY is 1, we are putting the data here. After that, at that time, PREADY signal should be 1 here. Okay, P enable is 1. At that time, we are maintaining the valid data. Then PREADY should be high. So during this phase, it is called as setup phase. We are selecting some slave. Okay, during the first cycle, so that is setup phase, that means T1 to T2, and then T2 to T3, that is transfer phase. Okay, or access phase. We are having the data here. Okay, after putting all the data, if you are having so once this is the data 1 and data 2, every data we need to maintain ready signal should be high here. Okay, you are transferring multiple datas, every data, when you are having every data, so I need to maintain enable should be high, and also select signal should be high, and also address is also valid address I want to maintain, and then data is 2 is there, and then ready signal also I need to maintain high. So this is without wait state. We are not having any wait state here. Now this is T0 to T1 cycle, all ideal signals. This is the ideal phase. Okay, that is default phase. There is nothing happened here. And then in setup phase, T1 to T2 setup phase, we are maintaining address is valid data, and write signal is high, and then select signal is high, enable signal should be 0. The next cycle, I am maintaining that, so address valid address, and then write is also high, and select is also high, enable signal also high. At that time I want to maintain valid data. So this cycle I am not getting any P ready high here. Okay, still the stable bus only maintaining the P ready signal. So that's why wait state is happening here. Ready signal is not high. Select is high, enable is also high, ready is not happening. Then only it is waiting. T2 to T3 to T4 is also wait state. Okay, we are also not getting um, P ready signal is high. That is also wait state. And T4 to T5, we are maintaining P write is high, P select is also high, and then P enable is also high, P data is also high, valid data is maintained, and then we are putting that ready signal should be high. The slave will be ready to receive the data, then only the data is transferred. That is the access phase. See, I told you that P clock signal. This is the clock signal. Okay, so T1, T2, T3, each and every clock cycle, we are toggling the clock signal. And then P address signal. That address is on bus. So at that time we need to maintain valid address. After that P write signal. P write signal, it is 1. Okay, you are doing the write operation. It is 0, you are doing read operation. And PWDATA. So that means data should be written into different devices like IO devices. Okay, it is supplied by the master or processor. Okay, master or processor are giving the data here, and then PWDATA is transferring the data here. That means we are maintaining valid data during write operation. After selecting the slave select, P select signal is there. Okay, this P select and P enable signal. So during write operation, we are maintaining the enable signal should be high. And P ready. So when you are getting the data, so we are having some data. Then P ready. So whenever you are getting your slave is ready to receive the data, at that time your P ready should be high. Clear? This is write transaction. You need to explain all these signals, how we are doing the write transaction. And also similarly, we need to explain the read transaction or read transfer. So here also two types of read transfers are there. One is with wait states and without wait states. With no wait states and with wait states. Setup phase, so every passage of the clock we are maintaining that signals are should be high. See here the first T0 to T1 we are in idle state. All signals P addresses should be 0 and then valid write signal should be stable state, not maintaining 1 here, and select is also 0, enable is also 0, and PRDATA is also not maintained, and PREADY is also not maintained. And T1 to T2 we are in setup phase. During setup phase we need to maintain valid address, and then you are doing read operation. That means P write should be low. Okay, so P write should be low means it is doing read operation. So reading will be happen here. Then I need to select the slave. So which slave I want to communicate it. That slave one will be maintained. Here enable is not there. Then valid data is not there here. So then setup phase is happened properly. After that, we are moving to access phase. In this access phase, we are maintaining P write should be low here. That means reading is happening, and valid address is also maintaining, and P select is also one, P enable is also one, and data maintain valid data. So at that time, we are slave is responding with P ready signal. P ready is high, then slave is ready to receive. Slave is ready to send the data to the master. Okay. So then this is without wait state. Now with wait states, so ready signal should not be high here. In the next cycle, it is also maintained. All the signals are valid signal whenever the data signal is one. So at that time only we are maintaining. We are giving the um, ready signal high. So that is called read transfer. Understood? What about the read transfer and write transfer? See, this is entire signals we are mentioning here. Write transfer and read transfer. All these signals. See, T1 to T2. How we are maintaining P reset signal should be low in the idle condition. So that means in reset condition it is operating. And P select is also 0. P enable is also 0. P address is also not maintained. And then P write is also 0 here. So not maintained high. And then PWDATA is also high impedance, and PSTRB is also high impedance. PRDATA is also unknown value, and then PREADY is also not giving high. PSLVERR is also low here, and PPROT signal high impedance value maintained. And wake up signals. These are optional signals. Wake up signal, PROT signal, APP user, PA user signal, that means APP5 signals. This is the APP5 signal, and PW user, that means write user signal. So these are all optional signals. If you want to maintain, you can maintain. Otherwise, not maintaining that. Understood what we are having the data. So same signals but different access we are having here. So setup phase, P-select signal should be 1 and P-enable signal should be 0. In the access phase, P-select is 1 and P-enable is 1. So idle phase, we are not maintaining the proper data. So we are having low data here. Okay. So again it is going to idle phase. After that address 2 we are sending, and then so at that time write signal should be 0, that means reading operation is happened, and data should be not valid here, and then strobe signal is also 0. After that PR data you are maintaining that data 2 should be valid data. PWDATA is not maintaining here. PRDATA is maintaining valid data. And then slave error ready signal should be high. After that, we are giving the slave error signal. That means, so slave error is happened means that is the last transfer. Whenever you are giving the last transfer, at that time only you are assigning that P slave error should be high. That is the valid reason. If you are mentioning slave error here only, then your read data should be invalid. Clear? So this is the setup phase, access phase, and idle phase. Error responses. So what we are giving the error responses? See, we are having P slave error. P slave error is the signal. So it is driven by APB slave. Okay, APB slave is driven that. So it is giving some error in your transaction. So if you are setting the P slave error that is sent by the slave, then error condition may be occur at the both write transaction as well as read transaction. During write also you are getting error, and then read also you are getting error. When P slave error should be valid. When it is valid means the last transaction only it is valid. See that at that time P select should be stable, P enable should be stable, and P ready should be very stable. So the last cycle only we are setting that P slave error should be 1. That is valid condition. See, P slave error is only considered valid during last cycle of your APB transfer. At that time, what we need to maintain high signals here, P select signal, P enable signal, and P ready signal should be maintained high. At that time only, we are considering that, okay, this is a slave error. That means you are not doing any transactions. And recommendation when not sampled. Okay, so that means you are doing the data, we are transferring the data, but that is not sampled. At that time also, we are giving that slave error data here. Okay, so recommendation of data. So when data is not sampled, so what happened here? Data is not mandatory, so it is recommended but not mandatory. That means slave error is low when it is not being sampled. If you are not sampling the data means that is not transferring the data, at that time slave error is low, that is okay. But during P select, P enable, P ready all are low, but you are setting P slave error should be low, that is not needed, right? Because you are not doing any transaction, that's why it is not mandatory signals. Okay, that gives no effect in your say, transaction. And then effect of error in error on transaction. What happened? So when you are getting the effect of error in your transaction, the transaction receives an error, might be or might not be changed. So that means your state of peripherals, what we are state we are accepting, that specifies here. Okay, you are doing write transaction or read transaction. Write transaction means in during write transaction you may not get, so that means during write transaction you are getting error means your register may having some fault data. Okay, your register may not be updated. Okay, not been updated, that is the problem. We are getting the slave error here, otherwise you are not getting any error. During read transfer, okay, read transaction that receives an error, that means it should be invalid data. during your read transaction you are getting error means slave error means then you are getting the data from the slave, that is invalid data. At that time error is considered here. In this time error is not considered during write operation. See, this is write read operation where we are getting the slave error here. This is my last transaction. Then you are putting the slave error should be high, and is also slave error should be high here. Okay, so that is the representation. And peripheral supports. See, P select, P enable, P address, P write. All these signals are sent by the master. Okay, P ready data, P read data, P ready, and P slave error. All these signals are sent by the slave. Clear? So now, what is the purpose we are using slave error here? Error condition we are using. So during write read operation, if we are getting any error, this slave error should be signal. This slave error signal should be maintained high. When it is valid means so P select, P ready, P select, P ready, sorry, P enable, P ready, all these signals are high. That is the last cycle of your transfer, then only it is valid. When it is not valid, so P select, P enable, P ready, all these signals are low means that is not valid and error. When effects on write transaction, error does not mean that registry is not updated. So your registry is not being updated. That gives also error during write operation. And read operation while you are receiving invalid data, that means you are getting some negative acknowledgement or slave error should be 1. So at that time read signal should be you are receiving a garbage value. See, APB pipeline, APB peripheral is a not pipeline signal and not also supports. See, it is APB peripherals are not required to support slave error. So sometimes we need to support and sometimes we need to, it doesn't require this slave error. Understood? What is the use of slave error? When you are getting the slave error, what is the valid condition of slave error? All these conditions you understood?
Sir,
Hmm.
in the timing diagram,
Hmm.
uh, when the slave error is high,
Okay.
uh, then only the slave error is the data is invalid.
Invalid. Yes.
But in the timing diagram,
Hmm.
there is no invalid, no sir. But why the error is came?
No, here what we are doing here, see, this is the last cycle we are mentioning. During the last cycle only, we need to mention the error signal. So that means you're receiving the data, nothing available here. You don't have any data to receive from the slave. Okay, at that time only we are putting this slave error should be high. Okay. So then at the time of read transfer only we are maintaining this slave error should be high. That means there is no other data in the slave side. Your master is all data is received from the slave. Then there is no data in the slave side means then we are putting the slave error. That means your slave is not ready to give the data to the master, right? Understood? Why we are putting the
Yes, sir.
slave error at the last cycle means so you have you have sending the data 10 transaction to your slave. Okay, so then all the 10 transactions are received by the master. Okay, then there is no data in your slave. If you are not having any data in your slave, then how you can ask the data from the slave and how you are getting the data from the slave? At that time, we are putting that slave error. That means, so that slave error indicates that there is no data available in your slave. Then the further transactions are not doing with that slave. That indicates that slave error. Understood?
Okay, sir. When there is no data,
Hmm.
the slave error is high.
High.
And also,
Hmm.
whenever the data is invalid,
Invalid. Yeah.
invalid means the error is high.
Yeah, error is high. See, during invalid data also you are putting the slave error. So during read transaction only you are so when you are keeping the slave error during read transfer, at that time invalid data you are receiving. At that time you need to check your data and where the error is getting. So is that doing data is properly is that giving data properly or not? We are checking on it. Clear?
Clear,
Uh,
sir.
so
Clear, sir.
then during write transaction, it is not valid because not mandatory we are considering because we only keeping the data into the slave. Then we are only keeping the invalid data means that is a invalid condition, not mandatory condition because we are keeping the data into the slave is a valid data. That's why we are putting that valid, we are maintaining stable valid signal, and then write signal is also stable, and select signal is also stable, enable signal is also stable. We are maintaining during write operation. That's why during write operation, if you are receiving any slave error, that should not be considered. Okay, here. Say this is the slave error signal representation while writing and reading transfers. Okay, so whenever PREADY is high, after that we are maintaining the slave error signal should be high. So that means slave error means so while when you are giving so some specific violation slave error response, that means slave accepts or completes the write. That means data 1 to address 1. So but signal failures via pay slave error should be 1. That means common cause is you are giving invalid address. That means so you are giving some P address should be address 1 should be some 1010 address you are giving. 4 tick binary you are giving. But you are getting the data from P address like 4 tick 1011 data you are getting. Okay, so then you are receiving garbage value because you are writing some data into the some particular address location, but you are reading the data in the next address location. Then address is invalid. That means you are practically you are getting invalid data. That means protection violation. That means uh, PPROT signal should be high. That means you are not getting okay response from the slave. You are getting some invalid data from the slave. Okay. So no master protocol violation. That means P address, P data, PW data should be stable during T2 to T3 states. That means see T2 to T3. So we are maintaining that. So P enable should be 1, and then PW data should be 1. See PW data where we are keeping the PW data here. So this is the PW data. PW data should be maintained high, and P enable signal also maintained high, and then P address is also maintained valid. So does not change that. During that only the protocol not violating. If you are changing this means your protocol violation will be happen. Okay. So these are the operating states. Okay. Just wait on it. Okay, fine. So these are the operating states in APB protocol. Ideal state, setup state, and then access state. So these are also called as phases also we need to mention. So ideal phase, setup phase, and access phase. So default phase is idle phase. Okay. So in APB protocol, idle phase means what are the signals we are maintaining? This P select signal and P enable signal should be 0. There is no transfer happened here during idle state. And if you are going for transfer means, so that means setup phase we are moving. In setup phase, the P select signal should be 1 here and P enable signal should be 0. Then it is moving to next state, access phase. During the access phase, P select is 1, P enable is 1. Then if your P ready is 0 means it is staying on the same state because ready signal is not 1 here. Okay, not 1 means we are waiting for that. We are waiting to receive that ready signal should be 1. That means we are waiting in a queue. So your slave should be send that ready signal should be 1. If you are sending ready signal 1 and then still there is another transfers are there, that means still some more transactions are happening, then it is moving to setup state. Okay, if it is moving to the setup phase means still I have another excess data, so I have some excess data. Okay, so that excess data I want to communicate it. Then after completion of all the data, if your ready signal should be 1 and there is no data transfer signals here, then it is moving to idle state. Okay, so it is moving to idle state and then so idle state means it is not doing anything. Then select signal should be 0 and then enable signal should be 0. P select and P enable signal should be 0. See, when transfer is required, P select should be elicited in the only one clock cycle. Okay, one clock cycle only it is asserting. And then in access phase, P enable is asserted. That means address, write, select, and write data remain should be stable. Up to that ready signal should be 1. So up to ready signal, if ready signal is low, still maintain stable here and then do not go to that idle state. If you are going idle state means your transaction will be lost. If your P ready should be high, okay, so and then no more data is there, then it is going to idle state. And then if your P ready should be high and then you are having more data and then more data is pending, then it is going to setup phase. Understood? So same thing here also we have mentioned idle phase. So P select and P enable should be 0. Okay, P select equal to 0 and P enable is also equal to 0. Then transfer is required and going to setup phase. In setup phase, P select equal to 1 and P enable is also 0. Okay, so then if it is moving to access phase, if you are doing if you are in wait state, then P ready should be low. If you are not wait state and there is no data pending, then P ready should be high and it is again going to idle phase. Or if you are having still some pending data, it is going to setup phase. Same thing here also explained. Default phase, no transfer is in progress. Both are select and signal enable signal should be 0. Select is accepted and control signals and address signals are driven here. Only one clock cycle data is happening here and the next cycle P enable should be 1. Okay, understood how it is happening here in the data transfer phase. So these are real-time soft uses of
Yes, sir.
these are the real-time soft uses of protocols, APB protocol. Where we are using real-time soft means, see, APB is an advanced peripheral bus used in real-time softs designed for low-speed, low-power peripherals communication. We know that low speed, low power, it provides simple, efficient interface to register access level and control and status registers, that means CSR purpose. It is more efficiently it is used. APB basically used for CSR purpose. control and status registers of the peripheral blocks. Whatever the peripheral blocks are there, all these peripheral blocks, it gives some status. Okay, I have done my operation, then I don't have any other data, so then I'm not involving any further transactions. At that time, the status signal should be high. So because you are receiving data and then there is no other data, then it is maintaining that high signal state. And then, so where the high level socks, CPU, they are DMA core, and in between that AHB or AXI bus we are using, and then there is a bridge, that is APB bridge. Okay, in this APB it is communicating UART, timer, GPIO, I2C, SPI, ADC, analog to digital communication, sorry, analog to digital conversion, and pulse width modulations and register transfer controls. Okay, APP is connected through bridge from high speed system bus to so through bridge only we are connecting. So where we are connecting high speed system bus like AHB or AXI, and it is used to access low speed peripherals and configuration also we are using configuration and configuration or status registers purpose also it is utilizing, and ideal for low bandwidth control oriented communication is there. See, common peripherals in using in APB protocol. What are the common peripherals? UART, timer, GPIO, I2C, SPI, ADC, and PWM, and then real-time clocks we are using. Okay, so all these are UART is a serial communication protocol, and timers we need to measure the time, and then where we are generating the clock for that purpose we are using timers, and GPIOs general purpose input output systems we are using. So I2C is a two-wire communication protocol, and SPI serial peripheral interface, analog to digital converter, pulse width modulations, and real-time clocks purpose we are using the common peripherals in your APB protocol. Why we go for UART? So what is the typical usage in real-time SOC? It it will debug console. Okay, UART will be UART tracer. So UART tracer is there that will trace the operation and then data logging and command interface. That purpose we are using UART, and delays in generation. Okay, so delays generation, that means is there any timeout issues are there or any periodic interrupts will be happening here, so that timer is measures that. And GPIO LED control, light emitting diode, so LED control, and then bottom input and interrupt triggers is also connected. I2C, I told you serial communication protocol, it is communicating with intra-band, short distance intra-band communication like sensor, CP-ROM, and then real-time clocks and peripheral controls. All these things are connecting through I2C. Serial peripheral interface, so it is used for flash memory, displays, sensors, high-speed peripherals, all these things we are using SPI. So ADC is an analog to digital converters for your sensors monitoring and then data acquiring purpose. So we are using ADC for ADC signals. And then pulse width modulation means motor control or LED damping, dimming. So and LED dimming purpose, that means low power consumption and then low power regulation purpose only we are using PWC pulse width modulation. You know that if your pulse is high, so your carrier signal should be high. Pulse is low, your carrier signal should be low. Okay, based on that we are measuring that controlling device, how the motor is controlling. This is the typical APB access flow in the register read or write operation. See, write operation, this is the CPU. CPU wants to write to peripheral registers. Okay, it is that it is want to write the data into the peripheral device. Then there is an AXI protocol. It is carrying the data from the CPU and transfer to APB. So it is setuping and then enabling phase, and then peripheral devices like UART, any other devices, it will have getting the data from the CPU. During register read operation, This data you are keeping into the register. Then CPU reads from the data from the peripherals. Then we are also having same AXI protocol and APB protocol. Then we are getting the data from the registers. That is the read-write operations. Because it is a non-pipeline protocol, so it is used to simple purpose only we are using it. Okay. So why APB bus is ideal for real-time SOCs? Because it is a low power, simplified interface. Okay, and fewer signals only we are using. Low bandwidth, and then low bandwidth requirement we are using. Some peripherals registers access purpose we are using low bandwidth. Simple and predictors purpose we are using APB protocol. It is a two-phase and non-pipeline. Protocol ensures the deterministic timing. So based on the timing only, it is getting the data. Easy to integration, real reliable. Okay. So why we are using APB protocol? Protocol is the reusable purpose and reliability purpose only we are using. These are the real-time examples, CPUs and AHP bus, APP signals, and then APP peripherals like UART, all these things. Understood? These are the key takeaways where the APP protocol is used in real-time stocks to low-speed peripherals and registers purpose we are using. And then this is the simple, low-power, reliable interface to control the status and registers for controlling status register operation. And ideal for UART, all these things. Okay. So this is the verification process, verification purpose perspective we are using. So if you know UVM, you will get to know all these things. Here UVM test and then how the test is happening, build phase, connect phase, run phase, and environment having scoreboard, agent coverage, virtual sequencer, all these things are connected to interface. After DUT is receiving the signals, and then agents we are having APP agent in that sequencer driver and interface signals are communicating. Okay, all these signals are connecting signals, and these are the interface signals like clock, reset, enable, data, all these signals. What is doing the driver sequencer is dating the data. In the sequencer, what type of data we are giving, randomization data. So this is if you know the test bench signals, and then you will get to know this all these things. Okay, typical test cases like basic write read operation, basic read operation, back to back transfers, wait states also used, and slave error signals we are implementing. Byte writes operation, that means strobe signals only we are using. Low power where we are using wake up signals, and then random or stress cases, and running during reset during transfers. Okay, during any reset during if you are transferring the data at that time, if happen any reset happens, then it is stopping the transfers. For that purpose we are using typical test cases. Okay, all these are typical test cases we are writing here. Okay, so scoreboard, what it is doing means expected data and then actual data, it is comparing that. So if it is matching, your test is passing, otherwise it is failing. In coverage closure, write, read, and then all bins we need to cover in the functional coverage, and then number of lines, how many lines are covered, it tells about the cross coverage. So some cross coverage we are having, functional coverage and cross coverage. That means transfer type and wait states, address and transfer types, strobes and transfer types, labor and transfer types. So all signals we are doing here. Okay, these are the assertions while doing some other operations. So these are also assertions related to APB protocol. So what phase transfer, setup phase, access phase, how we are data transferring, and then completion. So different signals we are using. This is the transfer signals we know already, right? And then APB protocol checks what we are checking. Select signal, and then so P select stable in access phase, that is happening or not. That means P select signal should be remain stable during access phase. So master or interconnect is applied here. So based on this, all signals we are checking. Similarly, P address signal should be stable during access phase. P write should be stable in access phase. PW data should be stable in access phase. P enable should be in access. So P enable signal should be 1 in access phase. So this access phase follows that all the signals are maintaining stable or not. We are checking that. If it is anything is not maintained stable, so the protocol violation is happens. Understood? So is there any carrying unknown value or high impedance on your signals? It can detect that. And then if slave error is only in the last cycle where we are getting P select, P enable, P ready, all are high. At that time you are having P slave error should be 1 or high. We are checking on that. And PR data valid when P ready is high. So then only it is valid data. Otherwise, we are getting some garbage value. So coverage points, write transfer, retransfer, write, wait state, slave error, back-to-back transfer, all these things we are checking that. And example write transfer, see, P select, P enable should be, P enable, P select should be 1, P enable 0, P write is 1, and P address is maintained, PW data is maintained, P ready should be 0, P slave error is 0, then setup is okay. So during setup phase, we are checking that. Access phase, idle phase. Understood? So this is differences between the APB4 and APB5. So some of the signals are there. So those signals only we are having. APB4 strobe signal is there, protect signal is there, wake up signal is there. In APB5, PR data is enhanced data is there. Up to 64 data is also it supports there. And then P ready is also enhanced. That is optional. That means slave to master we are having one signal. And P error signal. This is also optional. Okay. And then P user. So user signal. So where we are getting the signals. So that is also optional in APB5. So best just we are adding some signals compared to the APB4 and APB5. Here you can see the description here. Okay. What is the purpose we are using? And common APB principles. Non-pipeline, two-phase signals are there. Okay, simple interface, low power, transfer completion is enabled, P select, P ready should be high, and P lever indicates that error during the last cycle. Okay, these are the common principles we are following in APB4 and APB5 also. See, protect signal. P protect signal is that PROT signal 2 means security operations are there. If PROT 1 means privileged access. And then PROT 0 means some instruction access we are doing that. So this is the APB transfers happen. How the transaction is happening with the new signals. Okay. So these are the key benefits, efficient write operations we are doing, security protections, P by using prot signals, and low power signals we are also having wake up signal and PA user, and better reliability we are using. And then high performance also having in APB5. So because it is enhanced, right? 32 bit to 64 bit it is enhanced. So this is the complete overview. I told you, right? So APB architecture, high performance bus to AHB and then APB bus signal. So all low peripheral signals, all these signals are APB bus architecture. These are the key takeaways. So non-pipeline transfer signals, two-phase transfer, setup and enable phase. Every transfer at least takes 2 cycles. Address and control signals. These are the key takeaways in APB protocols. These are the signals P select, P clock, P ready, and then P enable, address, write, data, PR data, P strobe, ready, slave error, plot signals. All these are APB signals. Okay, and then write transfer is happening and read transfer is also happening. So write and read transfer is doing here. These are the key features already we have explained: non-pipeline, address control, slave latches, data transfer, ready signal should be 0 during wait state, ready signal should be 1 without wait state, and minimum cycles at least 2 cycles are there, and no burst transfers is supports. Okay, all these are overview of APB. So bus signals I have mentioned: clock, bus stable, high to low, low to high, bus to high impedance, all these signals. Okay, understood? And then these are the assertions. We don't know the asserts, right? So that will be not explaining.